chemistry time. Let's talk about, let's think about which title is correctly. Let's talk about nuclear radiation. Nuclear radiation. What am I probably going to do next? You've been here long enough. What's going to happen right after this?
You're going to go on a rant.
Today it's not the rant. You guys did a good job on your test.
You're going to give the definition.
Exactly.
Yep.
So let's talk about radiation first. What are some things that share the root word of radiation? You know.
Radiator.
Radiator. Yes, I don't know why you.
Radiant.
Everyone who, even those who aren't hillbillies, have to use radiators.
Radiant.
Radiant. Yes. What else?
Radio.
Radon.
Radio. Radon. Yes, all these are related, and I'm thinking of one specific other math one.
Ratio.
No. That
Radian.
Radians. Yes, that does come. That's not it. What?
Radius.
Radius, the radius. So all of these things relate to, actually, the root one is the radius of a circle. The radius is what we call it when something originates in the center and then moves out to the outside. Obviously, the radius itself is not in motion, but all of these things mean move out from a central point. How does that, let's go through our list now. How does that apply? Well, we'll get to how it applies to nuclear radiation. But how does that apply to a radiator? Like that one in the back there, you can't see on camera, for all you know it doesn't exist. But there's a radiator in the back.
That's the central point, and the heat comes out.
Yeah, exactly. The radiant, that's another word we use. The radiant heat comes out from that radiator. What about the radiator in a car?
The heat for your heater comes out of it.
Maybe, I don't know. I don't think so, not usually. But what it does do is it absorbs heat from the engine through conduction, and then it radiates that out to the environment to get rid of it. It helps the heat to be not stuck in your engine, which was causing it to overheat and burn. Nuclear, referring obviously, this one's easier, to the what?
Nucleus.
Referring to the nucleus of an atom. So we're specifically talking about energy and matter that move out from a central point, and that point being the nucleus of the atom. What kinds of, no, let's start with that. Let's start with what might cause nuclear radiation.
Chemical reaction.
Not chemical reactions.
Radioactive decay.
Yes, radioactive decay is another word for this. Thanks, Kyla. Radioactive decay. But that gives us a hint. The decay gives us a hint.
It's going to be
Electrons
with
leaving.
Not always electrons, but particles or matter. Particles or energy leaving the nucleus because of
unstable nucleus.
Exactly. Particles and energy. I'm going to put a slash because it could be both, it could be either. Particles and or energy leaving a nucleus due to nuclear, once again meaning what?
Nucleus.
Yeah, referring to the nucleus. Nuclear instability. And what causes nuclear instability? There's two things. We already talked about these in a different video, a different class if you're here in person, which many of you are. What causes nuclear instability? Great big nucleus? Because the strong force is a short-range force, and so it doesn't reach to both ends of the nucleus at once. Big nucleus or the wrong what? Wrong implies judgment, but yeah, let's say a certain ratio of what to what?
Protons to neutrons.
Yeah, protons to neutrons. That's because the neutrons interact only with the strong force. They also have mass, so strong force and gravity, but not the electromagnetic force. And the protons interact with all four of the fundamental forces, and so they repel each other, and if there aren't enough neutrons kind of in the mix to sell it. That's why, as we notice, some common isotopes, for instance, a very common isotope, probably the most common isotope in the universe is this one. Let's draw that real quick. What should be in the middle?
One hydrogen, one proton.
One proton surrounded by one electron. Probably the most common isotope in the universe. How many neutrons then? What's this one represent?
Number of protons.
No. In this case it does, but mass number is what it always represents. So then how many neutrons must it have? 0. It's just one proton. It's not being repelled by anything because it's just one proton hanging out. let's do another example. Another common isotope in the universe is this one. We did this one for part of our ballot. How should I draw the nucleus of that?
8 protons.
1, 2, 3, 4, 5, 6, 7, 8, and how many neutrons?
8.
1, 2, 3, 4, 5, 6, 7, 8. Electrons, doot, 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 doot. Oop, you're right, 6. Oh, I need to switch this to picture-in-picture so we can actually see what's on the board. Anyway, 1 proton, no neutrons. What's true of the protons and neutrons in this one? They're equal. They're equal. A certain ratio of protons and neutrons in this case being 1 to 1. Now we get a big ones. Another common nucleus in the universe, as far as radioactive ones go, is uranium-238. Uranium-238. That's not very common in the universe, but it's common as far as radioactive elements are concerned. That one's fairly common. Uranium-238. Well, how many because it's going to be complicated to draw it. Why?
Because there's so many.
So it's big, but also, let's just write the number: protons, neutrons, electrons. How many protons?
92.
You're right. How did you know, Mitch? He just made that number up and he happened to be right. He just played guess a number and he was right.
No,
No,
he looked at
wrong.
the atomic number.
The atomic number is number of protons. Every atom in the universe that has 92 protons is uranium, and every uranium atom has 92 protons. That's what defines a uranium atom. How many neutrons?
246. Or 146.
146.
Just do
Number of electrons?
92.
Thanks. Did you do that on your head pick? Ratio of protons and neutrons. There is none because there are no neutrons. Ratio of protons and neutrons? 1 to 1. And this one? It's getting pretty close to, it's really actually, it's almost 2 to 3. But you can see the ratio increases the bigger it gets because we have to have more neutrons to set apart the charge of the more protons. Do you see what I'm saying?
Yeah.
Also, this one is big, and so it falls into this category, so it's radioactive. Let's start with uranium-238 as far as radiation is concerned. As far as, I should say, specific types of nuclear decay are concerned. We use the word radiation in a couple different contexts in science. They're related, as they are to the math one, radius, but they're not the same. So we use radiation sometimes to mean, in fact, usually when we're talking in science, we mean radiation as in electromagnetic radiation, which is where an object emits or absorbs or reflects visible light, microwaves, gamma rays, those kind of things. Yeah? You're familiar with those. We'll talk more about them in the next chapter, but you should be familiar with those from physical science and 8th grade science. But then we also talk about radiation as far as nuclear radiation. And this can involve both particles and energy. And so we have these kind of, it'd be nice if there were different words for them. And so to specify, I say nuclear radiation or radioactive decay. And then for the other, I call it electromagnetic radiation. There is overlap. Which one? You know from your vocab. Which one is overlap between electromagnetic radiation and nuclear radiation? There's one thing that's the same in both. This is like a quizzable question as opposed to actually something you should know.
It was like 3 weeks ago.
Quizzable masters all that.
Oh, he probably knows.
Which type, to make it easier, which type of nuclear radiation is only electromagnetic radiation?
Electron.
No, electrons are particles, so it wouldn't be electron capture.
Fission?
Nope, that involves particles, a lot of particles. Gamma. Yeah, gamma rays are a type of light. They're electromagnetic radiation, and they're also nuclear radiation. They're not only nuclear radiation. Gamma rays can be released by other phenomena, like supernova, or even very, very hot stars. But they are also emitted by radioactive decay. Not this one. Get out of here, uranium. Not you. But some others. Anyway, let's start with uranium-238. I know for a fact, because this is one I use for an example very often, that uranium-238 undergoes what's called alpha decay. So let's have I like to build this chart. This is a chart that I use quite frequently, and I like it. We had, I think we decided, 6 types of nuclear radiation we're going to talk about.
Oh, perfect.
Nuclear radiation, she says sarcastically. What's
No, I mean perfect
It has a
because
problem
you keep
with
asking
it.
us these questions and I don't know.
Well, you're about to. Oh, so you're really excited.
Yeah, so I'm like legitimately
Oh, okay.
convinced at that time.
Okay. So we'll have a symbol Let's call this column symbol. Whoops. We'll have a name. We should have those the other way around. Hopefully no one's writing in pen. Let's have the name, then the symbol, then a description. Oops. Then a charge. That's way too big for the charge column. Erase. Then a mass. And then we'll have an example. I'll leave a lot of room for the example, and so should you do.
Is the name going to be pretty big?
No. I don't know. I mean, it depends.
Plus
Yeah, there'll be words. The name will be words as opposed to symbols. That's why we have a symbols column. 1, 2, 3, 4, 5, 6. I'm not going to bother drawing the lines because I'll mess it up. Let's draw them. Ooh, that one's good. That one started in the wrong
What's
spot.
after description?
Charge. This turned out pretty well.
Perfect.
So, okay. Let's do it in this order. Alpha, beta, plus, beta, minus, gamma, electron capture, spontaneous fission. Sometimes I feel like I'm going to spontaneously fizz. Okay, I wonder if the mic picked that up. It's okay, Mike, you're doing a good job. This guy's name is Mike over here. A little dusty. Symbol for alpha.
He had drawn dust particles.
Symbol for alpha.
The
Hey!
Anything? No.
The-
No. It's the
Yes,
alpha.
I draw it.
That's an alpha.
I don't want to draw it.
Let's also write this symbol for it, which is a Helium-4 Nucleus. You really have to squint to see that. I don't even think it's probably going to be visible on the computer. What it should look like this, I'm going to blow this up. F. That's not the letter F. There we go. This is an alpha particle. Alpha particle. And we use these symbols kind of interchangeably. It depends. This one will be more helpful for you, probably. Beta? Well, we can use the Greek letter beta, which is like a B with a tail, and then a little plus as a subscript, and same for minus. Also, for the plus one, we also use the letter E with a plus. What does E plus stand for? Does anyone remember? This is a trick question. I mean, not really a trick question. If you know it, you know it. What is it? Do you remember? It's a kind of what? Do you remember what kind of thing it is?
What do you mean?
It's a special type of... It's not matter. It's a special type of
Is that
thing in the
not-
universe that is... What? What did you say, Lou? It's antimatter.
Yeah.
It's antimatter. It's a positron. It's a positron. E plus stands for positron. The reason that the E plus stands for positron is because E minus stands for electron. And an electron has what kind of charge?
Neutron.
Here's a crash course on antimatter. Antimatter is normal matter. It's like normal matter, except everything is reversed. Antiprotons have a negative charge. They have the same mass as a regular proton, but they have a negative charge. Antineutrons are otherwise wild. They still have no charge. They still have no mass, but they still annihilate. And then positrons have a positive charge with the same mass as an electron, and they behave the same way. Antimatter, on the macro scale, should look and behave like normal matter, but all of the charges would be reversed, and if it interacts with, in any way, normal matter, it annihilates, and they become nothing except energy, which is
Bad.
Yeah, bad. This happens in nuclear decay on the atomic level, and so it's normally not difficult, but some news articles that I've read are saying things like, antimatter is the most expensive substance known to man. On the order of like thousandths of a gram can be produced, and it costs billions of dollars to do that. And so then they scale it up and they say it costs $6 trillion per kilogram. There's never been a kilogram of antimatter in one spot, because if there was, it would annihilate and it would vaporize everything for 200 miles. But it's like an electron, but has a positive charge. That's why it's called E+. It does happen, and it does exist. It's just existing all around us. It's just on such a minuscule scale that we don't even notice it. Gamma has a symbol gamma, which is kind of like, I don't know, this is how I draw it. Some people call it magenta. I don't know, look up you're already on the YouTube if you're watching this. Maybe Mr. Lover check out watching. That's a good idea. We could just have him watch this instead. I'll try that. Anyway, I'll cut this part when I do that. But switch to a new tab if you're watching this and just look up what the lowercase Greek letter gamma looks like, because it's kind of like that, but I haven't done it.
Like a Y?
Kind of. But it's kind of like a weird tailed Y, like that a little bit. Like it has a little loop-de-loop tail.
Oh, yeah.
You probably make your Ys like that already, I would imagine. Electron capture has a little curly E.
Curly?
It's even curlier. I think it might be the Greek letter epsilon. I haven't actually looked into that. Please don't at me. And then spontaneous fission is just big, bold SF.
What is the last name?
Spontaneous fission. You know about spontaneous. Like, a spontaneous human being does what?
Does
Doesn't
things out of
think.
blue.
Ooh, yeah, they do things. They start doors on fire.
Yeah.
Yes.
They go around with a pole saw and they manage to start a fire with it.
Spontaneous, what's the
They bring a duck call to school. That's a spontaneous person.
In the moment.
They live in the moment, yeah. There's a spontaneous fizzer out there. I can see him driving down the dirt road getting air. That's the kind of thing a spontaneous person would do. They'd be sitting on that couch one minute and they'd be like, I'm going to drive my Chevy Trailblazer 100 miles an hour down West Ash Creek. And then they would do it. That's spontaneous. Anyway, spontaneous in science means what?
Immediately.
Yeah. Kind of like a combination, kind of like halfway, like the average between immediate and random. You know, like it happens right away and all at once and not necessarily at any given time. So yeah. And then fission is what? What's a fissure?
I think it's swimming in the ocean.
That's a fish. That's nice though. What's a fissure? No, they're using a fusion. Fusion is when things fuse and combine. A fission is a breaking apart. A fissure, you can have a fissure on your lip, which is where it splits open.
Oh, I did know that.
Yeah, fissure or a fissure in the ground would be a crack in the ground. There's
Yeah,
an
like
opening.
when they talk about cuts, they.
Yeah. A fissure is a splitting apart. So spontaneous fission is where the atom, the large atom, just
randomly splits.
yeah, just falls not necessarily in half, but some ratio of protons and neutrons are left, and they always add up to the number of protons and neutrons that were there before, minus a little bit of energy, but they could be any random amount. And then those things usually spontaneously fizz or otherwise undergo radioactive decay because they're unstable too. Description. So alpha decay, we can put in here that it's helium nucleus. We already have that though, but helium nucleus. And then I like to include how we can stop this radiation. And alpha particles can be stopped by, they're the most massive, aren't they?
Yes.
The most massive, and they can be stopped by a sheet of paper. Sheet of paper. They're also, though, kind of, I don't know, not quite ironically, but interestingly, even though they can be stopped by a sheet of paper, they're the most dangerous ones if they are inside of you, because they're the most massive, they can do the most damage to DNA. That's why we consider this a dangerous thing. All of this is dangerous because if this, not all of it, but if some of this gets to you, I'm pointing at my arm because this is me, this is where I live, is in my arm, but if it gets to you, then your DNA, which is made of molecules, right, bonded atoms, can fall apart. It has enough energy to knock bits off your DNA, and if that happens in the right places, then your genome gets corrupted, and sometimes, most of the time, 99.99 whatever percent of the time, that cell just dies, which is bad, painful, depending on how much there is, negative in general, but the 0.00001% of the time, it doesn't die and it becomes cancer, and that's how come radiation is dangerous, because it causes what we call radiation burns and radiation sickness by cell death, and it also causes cancer for the cells that don't die. So it's dangerous to living things because of this. And alpha particles are the most dangerous because they're the most massive, so they can cause the most damage, but they can also be stopped by a sheet of paper. One demonstration that we're going to do later, depending on how much time we have, which is none, is we're going to have an alpha emitter, uranium-238, and we're going to open it up, and we're going to use the Geiger counter to see that there is alpha radiation. And then I wear goggles so I don't get eyeball cancer or my eyeballs don't get radiation burns, but they would if I didn't. But even my glasses would be enough to stop the alpha particles if I were looking in there. I wouldn't want to put my mouth in it because then I get in my mouth and I have living cells in my mouth. Your skin stops it. You'd be fine if it was like outside of you, but if it gets inside of you, not good. One of the reasons not to smoke cigarettes or vape the devil's jewel stick, don't do that, because tobacco, I don't know if the Lord just intended for the tobacco plant to be altogether evil, but tobacco concentrates polonium and other elements that are alpha emitters. So even if there's a tiny bit in the soil, there's quite a bit more in the tobacco plant. And then when that gets processed and all the water is removed, there's even more in the dried tobacco itself. And then you smoke it, and it hangs out in your lungs, and it just sits there and emits alpha particles all the time. So it's not just that tobacco is carcinogenic by itself, which it is, but also it emits alpha particles, which are the worst kind of radiation for being inside of you, which it is. Don't smoke.